In a previous video, we derived the formula for the sum of a finite geometric series, where a is the first term and r is our common ratio. What I want to do in this video is now think about the sum of an infinite geometric series. And I've always found this mildly mind-blowing, or actually more than mildly mind-blowing, because you're taking the sum of an infinite things, but as we see, you can actually get a finite value depending on what your common ratio is. So there's a couple of ways to think about it. One is you could say that the sum of an infinite geometric series is just the limit of this as n approaches infinity. So we could say what is the limit? What is the limit as n approaches infinity, of this business, of the sum from k equals 0 to n of a times r to the k, which would be the same thing as taking the limit as n approaches infinity right over here. So that would be the same thing as the limit as n approaches infinity of all of this business. Let me just copy and paste that so I don't have to keep switching colors. So copy and then paste. So what's the limit as n approaches infinity here? Let's think about that for a second. I encourage you to pause the video, and I'll give you one hint. Think about it for r's greater than 1, for r's equal to 1, and actually let me make it clear. Think about it for the absolute values of r's greater than 1, the absolute values of r equal to 1, and then the absolute value of r less than 1. Well, I'm assuming you've given a go at it. So if the absolute value of r is greater than 1, as this exponent explodes, as it approaches infinity, this number is just going to become massively, massively huge. And so the whole thing is just going to become, or at least you could think of it, the absolute value of the whole thing is just going to become a very, very, very large number. If r was equal to 1, then the denominator is going to become 0, and we're going to be dividing by that denominator, and this formula just breaks down. But where this formula can be helpful and where we can get this to actually give us a sensical result is when the absolute value of r is between 0 and 1. We've already talked about we're not even talking about a geometric series if r is equal to 0. So let's think about the case. Let's think about the case where the absolute value of r is greater than 0 and it is less than 1. What's going to happen in that case? Well, the denominator is going to make sense right over here. And then up here, what's going to happen? Well, if you take something with an absolute value less than 1, and you take it to higher and higher and higher exponents, every time you multiply it by itself, you're going to get a number with a smaller absolute value. So this term right over here, this entire term, is going to go to 0 as n approaches infinity. Imagine if r was 1/2. You're talking about 1/2 to the 100th power, 1/2 to the 1000th power, 1/2 to the millionth power, 1/2 to the billionth power. That quickly approaches 0. So this goes to 0 if the absolute value of r is less than 1. So this, we could argue, would be equal to a over 1 minus r. A over 1 minus r. So for example, if I had the geometric series, if I had the infinite geometric series, let's just have a simple one. Let's say that my first term is 1, and then each successive term I'm going to multiply by 1/3. So it's 1 plus 1/3 plus 1/3 squared plus 1/3 to the third plus, and I were to just keep on going forever. This is telling us that sum, this infinite sum, I have an infinite number of terms here. This is a pretty fascinating concept here. Will come out to this. It's going to be my first term. It's going to be my first term, 1 over 1 minus my common ratio. 1 minus my common ratio in this case is 1/3. 1 minus 1/3, which is the same thing as 1 over 2/3, which is equal to 3/2, or you could view it as 1 1/2. That's a mildly amazing thing.